In the course of quantum chemistry of atoms and molecules, some of us might be wondering, are we not wandering too far away from atoms? Because it has been a while that we have talked about atoms as such. Well, we will talk about a little bit of atoms in this module or the next, but what we are doing right now is that we are learning the tricks by which we can understand how to go about handling atoms and molecules for that matter. So, we have talked about perturbation theory so far, we will recap it in a moment. Today we are going to learn about perturbation theory of degenerate states. Of course, all of us know what degenerate states are. These are degenerate states, for example, states that have the same energy. Perturbation more often than not changes the energies of degenerate states with respect to each other. That is called lifting of degeneracy. So, you can think of such examples that you know, say Zeeman effect or Stark effect, application of a magnetic field or an electric field which changes the energies of orbitals that were earlier degenerate in such a way that they are no longer degenerate. So, this is one important reason why we must acquaint ourselves with perturbation theory of degenerate states. In fact, think of say metal ion complexes. Think of a free metal ion, all the d orbitals are degenerate. The moment you bring in this octahedral field or tetrahedral field or whatever field, the d orbitals split into 2 or more groups. So, lifting degeneracy is a very important thing that perturbations often do, but it is not necessary that degeneracies will always be lifted, as we will see in the 2 examples that we discuss in this context. In one, degeneracy will not be lifted at all, but the energies will be affected. In the other, some of the degeneracies will be lifted like what we have shown here. So, in this schematic we have taken 3 energy levels and we are saying that some kind of a perturbation affects the system in such a way that in the perturbed system 2 of the energy levels have lower energy and 1 energy level has higher energy, of course barycenter is same. Before we go there, let us remind ourselves briefly about what the salient points that we have learned in our discussion of perturbation theory of non-degenerate states. So, first of all we have learned that you have to write the Hamiltonian as the unperturbed Hamiltonian plus a perturbation term. We have written it in some other form earlier. Now, the form that we are dealing with, sorry about that. The form that we are dealing with now is this Hamiltonian of the perturbed system is unperturbed Hamiltonian plus lambda into V, where V is the perturbation potential and lambda is a parameter that we can regulate to increase or decrease the amount of perturbation that is there. And lambda finds its place in the expression for corrected wave function and corrected energy. Here we have lambda k is equal to lambda k 0th plus sum over j equal to 0 to infinity lambda to the power j multiplied by psi k jth. Similar expression for energy, we have learned this. We obtained this very important relationship, very important expression for the expression for the energy which is nth order correction to the energy. We learned this rather important expression for nth order correction to energy E k nth, and that is equal to integral psi k 0 star V psi k n minus 1th integrated over all space. Here if you put n equal to say 1, then the second wave function also becomes psi k 0th. Remember what k is, k denotes the energy level or the quantum number that decides the energy level. So, for hydrogen atom k is going to be n, for harmonic oscillator k is going to be V. Okay. So, this is the expression. We did not derive the expression, but we at least showed it to you and we told you that it is possible to come up with this 2n plus 1th correction term for energy in this manner. and we found an expression for this correction to wave function as well in this manner. Okay. Vik is this interaction integral we can say of involving ith and kth terms. Okay. Now when we go over to the degenerate states, then we encounter an interesting situation. Here for the kth level, that is for the level associated with energy say Ek 0th, we do not have one wave function. We have say n number of wave functions, we designate them psi k1, psi k2, psi k3, psi kn and so on and so forth. So please do not get confused here, in fact we are going to drop this k a little later. K here denotes the energy level. The second number denotes the index of the wave function, right. So you can think like this, think of hydrogen atom. In case of hydrogen atom, let us say we are talking about n equal to 2. In n equal to 2 you have several L levels, do not you. So I can have n equal to 2, and that means that the energy level we are talking about is E2 0th, and we have associated with n equal to, well I will make it simple, sorry, n equal to 1 let us say. And we have to write too many terms if it is n equal to 2. So, I will change it to n equal to 1. So, let us say n equal to 1, I have to change that as well. So, for that we know that L is equal to -1, 0, +1, right. So, how many energy states do I have, how many wave functions do I have, how many wave functions do I have, that is better, corresponding to this energy E1 0th. I have 3. So, I am calling them after this fashion psi 1 1, psi 1 0, psi 1 minus 1. If I write like this, that means I am writing in terms of NL. So, this is the psi NL form, or I could do something like this. I could simply not write L, but just write a sequence. I can simply say psi 1 1, psi 1 2, psi 1 3. So, 1 2 3 are well like roll numbers, indexes for the wave functions here. So, what I am saying here is that this -1, this is given the index 1, 0 let us say is given the index 2, 1 L equal to 1 is given the index 3, and so on and so forth. So, that is how we are writing. Okay. So, please do not get confused here. So, all these n number of wave functions that I have written here actually have the same energy Ek 0th. And of course, you can have wave functions that are not orthonormal to each other, but we can always take proper linear combinations and arrive at the orthonormal functions. And we have discussed many times why we like to handle orthonormal functions, because they are the coordinates. They are the functions that define the function space completely. So, we have to take complete set of orthonormal functions. Let us say this psi k1 to psi kn constitutes the complete set of orthonormal functions, all with energy Ek 0th. Okay. This is my unperturbed system, and this is the deviation from the case of non-degenerate states, remember. Let me erase this, because something is going to come up there and it is going to look very ugly. Yeah. So, it is a complete set of orthonormal functions, and the problem now is that I am not allowed to write the expression I wrote earlier. Psi k m cannot be written as psi k m 0th plus sum over j equal to infinity lambda to the power j psi k m jth. Why not? Because these are all indistinguishable from each other. I do not see a wave functions, right, I cannot see a wave function. How do I know which wave function I am handling? From energy, because energy is an experimentally measurable quantity. The problem is all these n number of wave functions have the same energy. So, we are back to that which is which kind of situation. Remember we had encountered this when we were talking about multi-electron atoms, when we have 2 electrons and we say that we do not know whether one electron number 1 is in 1s orbital, electron number 2 is in 2s orbital or the other way around, right. When we talked about helium ground state, excited state, we encountered such a situation. Here in a little different context we have the same thing. These wave functions are actually indistinguishable from each other because they are the same energy. So, if I write like this, then I am saying that this, let us take some wave function here. Let us say I am talking about, hopefully here nothing will come. So, I will write here. I want to know what is say psi 23. If I write psi 23 equal to psi 23 zeroth plus sum over all these things, then what I am implying is that out of all these wave functions only psi 23 zeroth, the zeroth order wave function psi contributes to the perturbed wave function psi 23. How do you know? Who has said that you cannot have any contribution from say psi 25 zeroth? Can I have a contribution from psi 1, okay, what is this 1 2 3 I wrote. So, can I have a contribution from psi 130th? Actually I cannot, because the moment I change the first index remember stands for k, the index of energy will change, it will no longer remain degenerate. But if I am talking about psi 23, there is no way in which I can say confidently that psi 23 will have contribution only from psi 23 zeroth and not from say psi 210 zeroth or psi 21 zeroth or any other wave function which has the energy E2 zeroth. So, what do we do in such a situation? Well, we do what we did earlier, we take a linear combination. What are the coefficients of linear combination? How do I find them? We will worry about those later. But to start with, the way to go is take a linear combination so that we do not rule out a priori the possibility that other indexes, wave functions, unperturbed wave functions with other indexes also contribute to this perturbed wave function. Okay. So, we take a linear combination like this, psi km zeroth is equal to sum over j equal to 1 to n psi kj zeroth Cjm. Cjm is the coefficient. Okay. So, what kind of coefficient? It is the contribution of the jth wave function in the among the wave functions that have energy k zeroth in the mth wave function of the newly created set, okay, and m of course has to be equal to 1 2 3 4 until n. So, just take a linear combination. Right now let us not bother about the form of the coefficient and how do we know it, and we will talk about it later. But if I write this, then I am safe. Psi km, the perturbed wave function, is equal to phi km zeroth plus this correction term. Okay. See, what I have done is in the correction term I have written it in terms of psi. It does not matter, it is okay. Okay. You do not have to write phi there, because after all phi is generated by taking linear combination of psi, and this is how we write the expression for energy also. Now, so what do I get? I get n number of perturbations, n number of expressions for this correction to energy. So, I get n number of wave functions which may or may not have the same energy, alright. When will they have the same energy? When all the energy levels or some of the energy levels are increased or decreased by an equal amount of energy as a result of the perturbation. When will they not have degeneracy? When different levels are affected to different extents. So, we will have a look at both kinds of systems. But before that, let us work out this nice expression. Okay. This is what we have. Now, what I will do is we will write the first order perturbation equation for degenerate states. You know how to write first order perturbation equations, we have done it earlier. So, I am skipping a few steps, but I hope it will not be a problem for anyone. So, this is what it is, h 0th minus E k 0th operating on phi k m 0th equal to E k first order multiplied by phi k m 0th minus V operating on phi k m 0th. Remember, I have jumped steps. So, I strongly recommend that you please work this out yourself, because otherwise when I say things in the flow of the lecture you feel as if you have understood everything. But then if you sit down with a pen and paper and try to work it out yourself, then if you do not have a question about how I have done things, that means you have not perhaps understood everything. You should be surprised, you should be puzzled, you should get confused, you should have questions, then only you will understand this. So, please work this out yourself, even though I have skipped it, you should not, and you should work it out after the fashion that we use for the non-degenerate case. Alright, so this is the first order perturbation equation. Let us see what we get from here. So, as usual, like what we did earlier, we are going to left multiply by psi k 1 zeroth, well, complex conjugate of that, and integrate over all function space. What do I get? I write psi k 0th, well, complex conjugate of that on the left hand side, integrate, that will be the left hand side. Right hand side, when I integrate, I get 2 terms. In one, this E k first is going to come out because it is a constant. Second one will involve a triple product, second integral of phi k 1 zeroth V and phi k m zeroth. So, this is what we get, okay, not very difficult to understand. Now what? What do we do now? Well, first of all, you might remember that this h 0th minus E k 0th is the annihilation operator not for the phi 0th terms, but for the psi 0th terms, right. And I can easily get psi 0th and phi 0th to interchange using a tool that is by now familiar to us, the turnover rule. Okay. So, when h 0th minus E k 0th operates on psi k 1 zeroth, I get 0. Then we do not even have to bother about the other wave function. So, left hand side is taken care of, that is equal to 0. What am I trying to do? I am trying to find an expression for the first order correction to energy. Great. Now, the next step obviously is to take this expression of the phi's, phi 0th, and plug it into these integrals. Okay. Plug in these linear combinations into these integrals, and this is what you get. Well, actually what I should also do is this. This coefficient is a constant, right. So, it has no business being in the bracket. So, we will bring it outside the bracket, but we will not bring it outside the summation, alright. Please do not forget there is this CJM, J is there. So, if you bring it out of the summation, then it has no meaning. So, we will not do that, we will bring it outside the integral, but inside the summation. Next, this one is going to become again phi k m 0th is replaced by sum over j equal to n, sum over j equal to 1 to n, phi k j 0th CJM. CJM is a coefficient, so I bring it outside the integral, but not outside the summation sign, alright. So, when we do that, we get this, well, we have to remember something. We have to remember that these psi's are actually your I should have written 0th everywhere, please forget, I mean please note that. But when we remember that these are actually orthonormal functions and when we plug them in, then what will we get? We will get something like this, right. We will get this, well okay, let us see what we will get. But before that, we will repeat the operation for 2, 3, 4 and so on and so forth. So, when we integrate over all function space, this is what we get. We get n number of what are called secular equations. Okay. So, remember there is one summation over j, right, that gives you from left to right of the left hand side of an equation. There is another summation over I, let us not forget that. So, this is what we get. Now, how do I solve this? Remember, to make things simple, we have written this as Vij and also we have written this first order correction to energy as x. Now, I hope you see that this x here is multiplied by delta Ij. Why? Because we are working with a complete set of orthonormal functions. So, when I is equal to j, then we are going to get 1. The integral will be equal to 1. When I is not equal to j, then the integral is going to be 0. Which integral? This integral, not this, because here you have this v in between. This one is going to be either plus 1 or minus 1, that is written as delta Ij. Okay. So, now this is what we have got so far, x equal to first order correction of energy and we want to find a better expression for that. Great. So, as we said, we have created this n energy levels, some of which may or may not be generate. Now, we write this n secular equations in the form of a matrix. Whenever we have a system of secular equations, we always write it in the matrix form, and when we do that, this is what you get. We get V matrix multiplied by C matrix is equal to C matrix multiplied by X matrix. What is V? V is the matrix whose matrix elements are the perturbation terms Vij. So, see how beautifully this problem gets formulated, it becomes a matrix equation. So, Vij essentially I and j denote the position of Vij in the matrix V, capital V. So, this perturbation takes up these Ij positions in the matrix. C's are called the eigenvectors. If you want to know more about eigenvectors, please go through our lectures on group theory in chemistry. So, eigenvectors are essentially coefficients. So, the coefficients are the components and capital X turns out gives us the values of the first order correction to the kth level energy, right, and this is also diagonalized. So, beautiful form can be solved by many different techniques, no worries really. Now, the field is set for discussion of 2 examples that we are going to do next day. But before that, the salient points, first of all, the degenerate states are such that several eigenfunctions can actually have the same energy. So, you cannot express a perturbed wave function as an unperturbed wave function just like that plus the correction term. You have to generate a linear combination of the unperturbed wave functions, from where we are going to begin, because there is no saying which unperturbed wave function has contribution in which perturbed wave function. It is not just a wave function and its perturbed form, they are indistinguishable. So, many can make contributions, that is point number 1. Point number 2 is when you accept that, you are going to get this very nice matrix equations in which these x values are going to turn out to be the x values here first order correction to energy. So, that is where we stop this module today. In the next module we are going to discuss hopefully 2 examples. One is non-rigid rotor, the other is star cap.